This is just a short video to demonstrate a trick I've been using recently while working with segmented memory on my Rigol DS2000. It should be applicable to the DS4000 as well, and perhaps the other Ultravision models. I'm not sure about that. As I'm sure many other owners know, working with segmented memory on the Rigol can be kind of challenging, partly because of the sheer number of frames you can capture, but also because of the lack of a built-in search function. For example, sometimes when you're doing protocol decoding for software debugging, you can set the trigger parameters to capture just the packets you need to solve the problem. But other times, because of intermittent or unpredictable behavior, you need to capture a lot of packets and then search through the segments for the source of the problem. This trick I'm demonstrating is a method for searching segmented memory by creating and altering masks. Now, normally, masks are used to locate anomalies or errors in a signal. And in fact, if you look at the mask and waveform as zeros and ones, you can see that pass-fail masks work like an AND gate, with a logic 1 result meaning an error or fail. But if we just invert what our desired result is, then instead of using masks to locate errors or failures, we could instead be using them to locate passes, or in other words, matches in our searches. For the following example, imagine I have a problem on an I2C bus. The control status register in one of the chips is being overwritten with bad data, but the problem is intermittent. The incorrect data is constantly changing, and the control register is also being written correctly from time to time. So I want to capture as many segments of I2C packets as possible so that I can examine what's happening on the bus before and after any of the bad writes. And once I've recorded thousands of segments, I want to quickly find each write of the control register and check if it's correct. So in this example, the register is memory location 0 at the chip address of A0 hex. So I've got my oscilloscope hooked up to the I2C circuit. I've got channel 1 connected to the data line and channel 2 connected to the clock line. I've got my I2C bus decode turned on, and I'm going to set up the trigger now. Again, I want to capture a write of 00 to the location A0, so I'm going to set the trigger to trigger on address and data. My address is, well, it's 1 bit shifted over, so that would be 60 in hex or 80 in decimal. We'll get that set up. Okay, it's the address and the data. So down here, we're looking for 0, so all low. So we'll move that to low and set all bits. And that takes care of our trigger, and we can go into normal mode now, and we're going to capture an occurrence of that. So you can see that I've captured an occurrence of the writing of 00 to A0, and I'm going to stop the scope now. And now I want to create a mask from this one particular packet. So I'm going to expand it until it pretty much fills the display. So we'll go a little bit bigger that way. I think we have to use the fine adjust. Make it farther. Move that out of the way. And we'll set it so the first falling edge is right at the border here. That'll make it easier later to line it up. And that's the last rising edge. So that's what we want to create the mask from. So now we go into pass-fail. We turn on pass-fail. Make sure that the source is set to the channel which you want to search for later. In this case, that's my data channel, so that's correct. I'm going to go to range. Now, with the range, the X should be as pretty much as tight as possible this way horizontally, so that we make sure we only match
the particular data that we want. But the Y mask, the vertical, should be bigger than, whoops, I'm on the wrong one. It should be bigger because you want to make sure you encompass any possible overshoot that might happen. So we'll make that around there, create the mask. Okay, and now we would save this. And I've got some already saved on here. You can see I've labeled them with the bus name, the name or the size of the time base, 25.4 microseconds, write to A0, the data 00, and then in this case it's data 04. So this is this write to A0 chooses the memory location 00, and then it's writing a 04 in there. And in this example that we're kind of posing here to demonstrate this, somehow the software is writing to this control register some bad data at some point, but it's intermittent. So what we want to do is we want to create a mask that basically is the write A0 of 00, and then this section, what would be the next data, we want it to be an all-inclusive mask that it would match anything possible in this spot. Of course, that's impossible to do with the Rigol, but we can manipulate the mask on the PC and then bring it back to the Rigol so that it matches what we really want to be searching for later on. So I'll show you how to do that in a second. Let's just assume we're saving the mask here. So you would save it, we'll overwrite that, and then it's done. Now from here we go, you can turn off the pass fail enable, and we're going to go to the PC now.
So before we edit the mask file, I wanted to go over the format of Rigol mask files. And for the DS2000 and 4000, these mask files are always 1414 bytes. They consist of a 14-byte header followed by 2 bytes for each horizontal screen pixel. So that's 2 times 700. And those bytes specify the endpoints of a vertical line which defines the open area of the mask for that pixel column. So in fact, what you're actually looking at in the file is rather the inverse of the mask. Now the functional lowest and highest values for the endpoints of those lines match how the DSO maps the ADC to the display. So on the DS2000 it maps 200 values, so that the lowest point on the display here is the value 28 or 1C in hex, and the highest point is 227 or E3 in hex. And on the DS4000 it maps all 256 values to the display, so you have 00 to FF completely. And lastly, the first and last pair of coordinates in the file are always 00FF, so it always creates a kind of border along each horizontal display edge, perhaps to prevent erroneous fails of the mask. But those are always the beginning and ending of this 1400 bytes. So here we are looking at the mask file in hex editor. You can see that the 14-byte header is up here at the beginning, and there's the first line of display data, the 00FF, and here at the end of the file, again, the 00FF I mentioned before. On this side of the screen, I've got a screen print of the mask that we created. So this is the mask that we're looking at here in the hex editor. So what I want to do for this particular example is I want to enlarge the mask so that any data byte that arrives here will be matched. So that requires, you can imagine probably, that requires that this whole area here is one big block of open area on the mask, because these are the data bits coming in. That last bit is the acknowledge bit, that has to be low as well. So if we create a block of open area here, any high or low bit will automatically match. So looking at the hex file, if you glance at it and you look at the screen print, you can kind of see the patterns emerge. For example, every time the mask has an open area up near the top of the screen, there are these kind of stripes of high hex numbers. So for example, CC to E1 is probably right around there, CC to E1. It's that size. And anytime there's a kind of block of these lower numbers, for example, 51 to 66, that means it's this area down here. So basically what I want to do is right where this edge falls here, that's one long stripe of open area, and I want to copy and paste that all across this block. So that edge is probably something from about 50 hex up to about E1, like we said. So and it's going to be the 6th edge from the end of the file. So we can count from this to this is 1 edge, from the low to high 2nd edge, high to low 3rd edge, 4th edge, 5th edge. So this is the 6th edge here. So if I look, I can see right here we have 50 to E1. That's that entire straight edge, because the next byte after that is 50, 65, so then it's low again. So I'm going to mark this block, and then I'm going to paste it down this line. I think it's get a whole line of them. Then I will mark that entire line. And start pasting this way. Whoops. Just want to make sure we don't go too far and lose edges that we want. So let's see where we are. 1, 2, we're near the 3rd edge. 1, 2, okay, we're just coming up on this edge. We just want to follow through to that. We can paste there, and this one 50E1. That's that falling edge. Okay, I think that does it. I think I'm on the other side of that edge. That should do it. So I'm going to resave this file. And we're ready to go back to the scope.
Okay, now we're back at the oscilloscope. We've created our altered mask, and now it's time to actually capture the segments, the frames that we want to search through. So the first thing that I would do now is change my I2C trigger to start bit, so it's capturing all the packets. I would shift the trigger point, because before it was triggering after the address data signals came in. Now we want to trigger on the start bit, so the trigger should be over on the other side of the screen, somewhere around there. And we're ready to go, so we're just going to start it up. Okay, so I've got the scope set to normal trigger mode. I've got the recording segment feature armed, and I've adjusted the memory size to 7 kilopoints so that we can capture a lot of frames. So I've captured 204 frames. I'm in playback mode now. You can see I can flip through them here. I could go through them one by one and look for all of the, writes to A0 with a 00, but instead I'm going to use my mask. So I'm going to enter analyze mode. We're going to turn on the time tag. Okay. Now we want to be in pass-fail, and we want to load our mask from the USB stick. That's this one, the D --. Okay. Now you can see we're not exactly lined up to the A0 part of the data, so we can adjust our horizontal position till we get lined up there. Whoops. Be right near the edge of the screen. Okay. Now you can see there's the mask we altered. We made that area completely open so that any kind of data here that's written will be a match anyway, so we'll find every time that A0 is written with 00 and then another byte. But you see right now we've got on the first frame we've got the addressing of that memory location, but then it's a read from there. But you see we won't match reads because they have the delayed clock line, and so you can see that the final edge of this packet runs outside or runs through the mask there. So in fact, this won't be a match for it. So anytime it's reading actually that location, we won't match. We're only going to match when it writes it. So we'll start the analyze going and see what happens. And let this clear. You can see it looks like we've got 4 matches. Yeah, it says of the 204 frames, 200 it says are error frames. In fact, those frames are fine, they're just not matched. Those are our 4 matches, so we can scroll through them here. Unfortunately, the Rigol decoding doesn't work inside of analyzing, so we won't be able to see the decoding of it, but we can get the frame numbers. So let's see, that is frame 91. You can see that we're within the boundaries of our mask there. Frame 93 and 107 and 109. So those were the 4. I mean, obviously I only had 204 frames. You could have 800, 1,000, 10,000 frames, and it's going to find every match where the location 00 is written to with a byte of data at the chip A0. So anyway, that should give you an idea of how to do it. It doesn't have to be with buses only. You can, any kind of segmented memory that you can capture, you can create masks and alter them to search for stuff. Hopefully, my plan is the next version of RUU, my Rigol utilities, Rigol Ultravision utility software that I've been writing. You'll be able to make masks in that software and alter them graphically, with a mouse. So it'll make it a lot easier. You can read them out of the scope and then write them back to the scope. So hopefully that will be coming in the next version. But meanwhile, this is a way to do it manually, and hopefully it'll be helpful to some people. Okay, that's all for now.